This video contains audio content only. There are no visual elements or images accompanying the audio. If you're expecting to see video footage, please note that this is an intentional audio-only presentation. We recommend listening to this content rather than watching the screen. Thank you for your understanding and enjoy the audio. Welcome to our exploration of the fascinating world of bananas. In this video, we'll take you through the rich tapestry of scientific discoveries, stories of agricultural ingenuity, and environmental insights behind one of the world's most beloved fruits. By delving into the recent research across botany, ecology, and genetics, we aim to uncover how bananas have evolved, thrived, and, at times, struggled within a changing global landscape. Staying up to date with scientific advances not only benefits professionals but also offers enthusiasts a deeper appreciation of the intricate dynamics at play in our food systems. From the intriguing history of the Gros Michel and the rise of the Cavendish to challenges like Panama disease and the importance of genetic diversity, we'll explore what makes the banana both resilient and vulnerable in today's world. So, whether you're here out of culinary curiosity or scientific interest, prepare to gain a fresh perspective on how nature, science, and human ingenuity converge in the journey of the banana. Chapter 1. The Reign and Ruin of the Gros Michel, a Banana's Tale. Imagine biting into a banana, but not just any banana. This isn't the Cavendish banana you find in every grocery store today. This is the Gros Michel, the Big Mike, a banana that once ruled the world's fruit bowls. It was a different era, a time when bananas were a taste sensation, a luxury, a symbol of the exotic. The Gros Michel, with its unique qualities and compelling story, offers a glimpse into a bygone era of banana history and a cautionary tale of agricultural practices. The Gros Michel's rise to stardom began in the late 19th century. It wasn't just a bigger banana, it was, many argue, a better banana. Its flavor was richer, sweeter, with a pronounced aroma that hinted at vanilla and pineapple. The texture was described as creamy, almost like custard, a far cry from the sometimes starchy Cavendish. And its thick peel? That was its golden ticket to global domination. In the days before refrigerated shipping containers, this resilient peel protected the delicate fruit during long sea voyages, making it the perfect candidate for international trade. The early banana trade was a wild west of entrepreneurs and logistical nightmares. Transporting a delicate tropical fruit across vast oceans presented enormous challenges. Bananas ripen quickly, bruise easily, and are susceptible to rot. How do you get this fragile fruit from the tropics to temperate climates in edible condition? It was a puzzle that captivated and challenged early banana traders. One of these pioneers was Lorenzo Dow Baker, a sea captain from Cape Cod. In 1870, Baker loaded his ship with 160 bunches of Gros Michel bananas in Jamaica, a gamble that would change the course of banana history. He sailed to New Jersey and, to his delight, the bananas arrived in surprisingly good condition. He sold his cargo for a staggering $6,400, a fortune in those days, equivalent to over $150,000 today. This success wasn't just luck, it was a testament to Baker's ingenuity. He had discovered that picking the bananas green and allowing them to ripen slowly during transport was the key to preserving their quality. Baker's success sparked a banana boom, and his Boston Fruit Company quickly became a major player in the burgeoning industry. They perfected the art of banana transport, developing specialized ships with ventilation systems and carefully controlled temperatures. They even experimented with early forms of refrigeration, constantly innovating to minimize losses and maximize profits. But getting the bananas to market was only half the battle. They also had to convince people to buy them. And at $2 a bunch, about $50 in today's money, these weren't your everyday fruit. Bananas were a luxury, a treat, a taste of the exotic. The Boston Fruit Company's dominance wouldn't last long in its original form. In 1899, it merged with the Tropical Trading and Transport Company to form the behemoth known as the United Fruit Company. This wasn't just a merger, it was the creation of a banana empire. United Fruit controlled vast plantations in Central America, a network of railroads and steamships, and a significant portion of the banana market in the U.S. They weren't just selling bananas, they were shaping consumer demand. Through clever marketing campaigns, they transformed the banana from an exotic luxury into an affordable, everyday staple. They touted its health benefits, its convenience, its versatility. They even created recipes and distributed them to housewives across the country. United Fruit wasn't just a company, it was a force of nature, and the Gros Michel was its flagship product. But the Gros Michel's very success, fueled by United Fruit's relentless pursuit of efficiency and standardization, would ultimately lead to its downfall. To ensure consistency and maximize profits, United Fruit embraced monoculture farming. Vast plantations were dedicated to a single variety, the Gros Michel. Every banana was a clone, genetically identical to its neighbor. This created a landscape of uniformity, a sea of green banana plants stretching as far as the eye could see. It was a system designed for efficiency, but it was also a system ripe for disaster. A single disease, a single pest, could wipe out everything. And that's precisely what happened. In the 1950s, a soil-borne fungus called Fusarium oxysporum F. sp. Cavendish *, better known as Panama disease, swept through the Gros Michel plantations. This fungus is a particularly insidious foe. It enters the banana plant through the roots and colonizes the vascular system, the plant's circulatory system. It blocks the flow of water and nutrients, effectively choking the plant from the inside. The symptoms are unmistakable: yellowing leaves, wilting foliage, and a gradual decline that ultimately ends in the plant's death. The fungus produces chlamydospores, hardy resting spores that can persist in the soil for decades, making eradication virtually impossible. The impact on the banana industry was devastating. Plantations were decimated, economies were disrupted, and the Gros Michel, once the king of bananas, began its slow, tragic decline. By the 1960s, it was commercially extinct, a victim of its own popularity and the monoculture farming practices that had propelled it to global dominance. The reign of the Gros Michel was over, leaving behind a legacy of flavor and a cautionary tale for future generations. The story of the Gros Michel is more than just a banana's tale. It's a story of human ingenuity, ambition, and the unintended consequences of our interactions with the natural world. Chapter 2. A Balancing Act: Genetic Diversity and the Future of Bananas. Imagine strolling through a vibrant farmer's market, a cornucopia of colors, shapes, and sizes bursting from every stall. Apples in shades of crimson, green, and gold. Tomatoes ranging from plump heirlooms to sweet cherry varieties. Now, picture yourself in the banana aisle of your local supermarket. A sea of yellow Cavendish bananas, virtually indistinguishable from one another. This stark contrast highlights a critical issue in our food system: the dominance of monoculture farming, particularly in the case of bananas, and the potential consequences of this limited genetic landscape. Monoculture, the practice of growing a single crop variety across vast areas, is the driving force behind the banana's uniformity. While seemingly efficient, this practice carries a significant risk. It creates a system akin to a house of cards, easily toppled by a single gust of wind, in this case, disease. If one plant in a monoculture is susceptible to a particular pathogen, the entire crop becomes vulnerable. This isn't a theoretical threat. It's a historical reality for bananas and a looming danger for the Cavendish, the banana that currently dominates the global market. To understand the genetic makeup of bananas, it's helpful to delve into the A-B genome system used to classify banana cultivars. These letters represent the genetic contributions of two wild banana species, Musa acuminata, A, and Musa balbisiana B. The Cavendish, for example, is a triploid AAA, meaning it has 3 sets of chromosomes all derived from Musa acuminata. Other varieties, like the plantain, often used in cooking, are typically AAB, indicating a contribution from both wild species. The variety of genome combinations leads to a spectrum of fruit qualities, from the sweet dessert bananas we typically eat raw to the starchy plantains that require cooking. The Gros Michel, the banana that preceded the Cavendish in popularity, was also in AAA triploid. This seemingly minor detail holds a crucial lesson. The Gros Michel's reign ended abruptly in the mid-20th century, felled by a soil-borne fungus called Panama disease, or Fusarium wilt. This fungus, Fusarium oxysporum F. sp. Cavendish *, invades the plant's vascular system, disrupting the flow of water and nutrients, ultimately leading to the plant's demise. Because all Gros Michel bananas were essentially clones of one another, they shared the same susceptibility to this particular strain of the fungus, race 1. The disease spread rapidly through plantations, decimating the Gros Michel and nearly driving it to extinction. The Cavendish, resistant to race 1, emerged as a savior, filling the gap left by the Gros Michel. However, the Cavendish, too, is a monoculture, propagated from offshoots rather than seeds, making every Cavendish banana a genetic replica of its neighbor. This lack of genetic diversity creates the same vulnerability that doomed the Gros Michel. This monoculture practice isn't unique to bananas. Coffee, for example, is another crop heavily reliant on a small number of varieties, making it similarly vulnerable to disease and climate change. The Arabica and Robusta beans that dominate the market originated from a handful of plants, limiting the genetic diversity needed to adapt to evolving threats. Just as the Cavendish banana faces potential devastation from tropical race 4, a new strain of Panama disease, coffee's future is threatened by changing climate conditions and emerging diseases. The challenge of breeding new, disease-resistant bananas is compounded by the seedlessness of commercial varieties. Because the Cavendish doesn't produce viable seeds, traditional crossbreeding techniques are difficult. Scientists are exploring other approaches, such as genetic modification and gene editing, but these methods face regulatory hurdles and consumer resistance. Maintaining diverse gene banks, repositories of wild and cultivated banana varieties, becomes crucial. These gene banks preserve the genetic diversity that could hold the key to future disease resistance and adaptability. Researchers are actively exploring the genetic material of wild banana species, searching for traits that could be incorporated into new, more resilient varieties. One such wild species is Musa gracilis *, a small banana native to peninsular Malaysia. This species, growing less than 2 meters tall, produces narrow fruits filled with tiny black seeds, a stark contrast to the large, seedless Cavendish. Another intriguing example is Musa ingens *, the largest herbaceous flowering plant, found in the jungles of New Guinea. This giant banana can reach heights of 45 feet, its towering pseudostem made up of tightly packed leaf sheaths. Researchers like Joseph Simcox, who has traveled extensively to study wild bananas, have documented the diverse uses of these wild species by indigenous communities, highlighting their potential for future domestication and the importance of preserving their genetic heritage. The current threat to the Cavendish comes from tropical race 4, a strain of Panama disease that overcomes the Cavendish's resistance to race 1. This soil-borne fungus spreads through infected soil, water, and even on farming equipment. Just a few spores can contaminate a plantation, making containment extremely difficult. The fungus invades the plant's roots, colonizing the xylem vessels that transport water and nutrients. The plant wilts, its leaves yellow and eventually die, halting fruit production. While not harmful to humans, the disease is devastating to banana crops, threatening the livelihoods of millions who depend on banana farming. Scientists are not only working on breeding resistant varieties but also exploring other avenues to combat Panama disease. Research on the banana microbiome, the community of microorganisms living in and around the plant, is shedding light on the complex interactions between the banana, the fungus, and other microbes. Studies have revealed shifts in the banana's microbiome in response to Panama disease infection, suggesting that manipulating the microbial community could be a potential strategy for disease control. Another challenge in diversifying the banana landscape lies in consumer preferences and retailer practices. Consumers have become accustomed to the Cavendish, its consistent size, shape, and flavor. Introducing new varieties, which might look or taste different, requires overcoming this ingrained preference. Retailers, too, are hesitant to stock a wider range of bananas, fearing consumer rejection and the logistical complexities of managing multiple varieties. However, consumer choices can play a significant role in shaping the future of the banana. By seeking out and purchasing different banana varieties, when available, consumers can send a signal to retailers and growers that there is a demand for diversity. This, in turn, can create incentives for farmers to cultivate a wider range of bananas, fostering a more resilient and flavorful banana landscape. The story of the banana is a powerful illustration of the delicate balance between efficiency and resilience in our food system. The pursuit of a single, perfect, banana, optimized for mass production and global trade, has led to a precarious situation where a single disease threatens the entire supply. By embracing diversity, both in our banana choices and in our broader agricultural practices, we can create a more sustainable and flavorful future, not only for the banana but for our entire food system. Chapter 3. The Cavendish and the Threat of Panama Disease. Panama disease, a formidable foe of bananas, casts a long shadow over the future of our favorite fruit. Let's delve into the science behind this disease and understand why it poses such a challenge. Panama disease, also known as Fusarium wilt, is a fungal infection that spells disaster for banana plants. The culprit is a soil-dwelling fungus with the scientific name Fusarium oxysporum F. sp. Cubens *FOC. This fungus is a master of stealth, lurking in the soil until a susceptible banana plant comes along. It then infiltrates the plant through its roots, gaining access to the plant's vascular system, the network of vessels that transport water and nutrients throughout the plant. Think of the banana plant's vascular system as a series of tiny pipelines. Once inside, the fungus begins to colonize these pipelines, effectively clogging them up. This blockage disrupts the vital flow of water and nutrients from the roots to the rest of the plant. The initial symptoms are a telltale yellowing of the leaves, particularly the older ones. As the disease progresses, the leaves begin to wilt and eventually collapse entirely. In some cases, the banana heart, the precursor to the fruit bunch, may fail to emerge from the pseudostem, a phenomenon known as choking. Ultimately, the entire plant succumbs to the infection and dies. Adding to the difficulty of controlling Panama disease is the fungus's remarkable ability to survive in the soil for extended periods, even in the absence of a host plant. FOC produces specialized survival structures called chlamydospores. These are like tough, microscopic capsules that protect the fungus from harsh environmental conditions. Chlamydospores can lie dormant in the soil for decades, waiting for a susceptible host to appear. This makes it incredibly difficult to eradicate the disease from contaminated land, as the fungus can re-emerge at any time to infect new plantings. Now, here's where things get even more complicated. Panama disease isn't a single, monolithic entity. The fungus exists in different strains, often referred to as races, each with its own set of characteristics and host preferences. Two races of FOC are particularly relevant to the story of the Cavendish banana: Tropical Race 1, TR1, and Tropical Race 4, TR4. TR1 was the strain responsible for the near extinction of the Gros Michel banana, the dominant commercial variety in the first half of the 20th century. Gros Michel plantations were devastated by TR1, leading to the banana industry's desperate search for a resistant replacement. Enter the Cavendish. This variety, though smaller and less flavorful than the Gros Michel, possessed a crucial advantage: resistance to TR1. This resistance allowed the Cavendish to thrive in soils contaminated with TR1, and it quickly became the new global standard. However, the Cavendish's triumph was short-lived. A new threat emerged in the form of TR4. This strain of the fungus not only overcomes the Cavendish's resistance but also poses a danger to many other banana varieties, including local cultivars grown in various parts of the world. So, while the Cavendish replaced the Gros Michel because it could withstand TR1, it is now facing its own nemesis in TR4. The spread of TR4 has been alarmingly rapid. First detected in Southeast Asia in the 1990s, it has since marched across continents, infecting banana plantations in Australia, Africa, the Middle East, and most recently, South America. The ease with which TR4 spreads contributes to its devastating impact. The microscopic chlamydospores can be carried on contaminated soil, clinging to tools, machinery, footwear, or even clothing. A single contaminated item can introduce the fungus to a new area, where it can quickly establish itself and spread to susceptible plants. Currently, there is no known cure for Panama disease, and no effective treatment to save infected plants. Fungicides and other chemical treatments have proven largely ineffective against TR4. While bananas harvested from infected plants are safe to eat, the plants themselves are doomed. They eventually stop producing fruit and die, halting future production and causing significant economic losses for farmers and communities that depend on banana cultivation. The Cavendish banana's vulnerability to TR4 stems from its unique reproductive strategy. Unlike wild bananas, which reproduce sexually from seeds, Cavendish bananas are propagated asexually. This means that new plants are grown not from seeds but from offshoots, or suckers, that emerge from the base of the parent plant. Each new plant is essentially a clone of its parent, genetically identical in every way. This lack of genetic diversity is a major weakness. In a population of genetically diverse individuals, some may possess genes that confer resistance to a particular disease. These resistant individuals can survive and reproduce, passing on their resistance genes to their offspring. However, in a monoculture of genetically identical clones like the Cavendish, if one plant is susceptible to a disease, all are susceptible. There is no variation, no chance for natural selection to favor resistant individuals and strengthen the population's overall resilience. Scientists are exploring various approaches to combat Panama disease and protect the future of bananas. One avenue of research involves genetic modification and gene editing. These techniques aim to introduce resistance genes into the Cavendish banana or modify existing genes to enhance disease resistance. However, this approach faces challenges, including regulatory hurdles for the approval of genetically modified crops and consumer concerns about the safety and environmental impact of GMOs. Many countries where bananas are a staple food crop have strict regulations or outright bans on genetically modified organisms, making it difficult to deploy these solutions on a large scale. Another strategy involves exploring the vast genetic diversity of wild banana species. Although many wild bananas are inedible due to their abundance of hard seeds, they may harbor genes that confer resistance to TR4 and other diseases. Researchers are working to identify these resistance genes and introduce them into cultivated varieties through traditional breeding methods. However, breeding seedless banana varieties is a complex and time-consuming process, as it requires overcoming the inherent challenges of working with sterile triploid plants. The goal is to develop new banana varieties that combine the desirable traits of the Cavendish, such as its sweetness, size, and suitability for shipping, with the disease resistance of wild bananas. Chapter 4. The banana's global reach, from staple food to economic engine. Bananas. We grab them on the go, slice them into our cereal, blend them into smoothies. They're so common, so readily available, it's easy to forget just how vital a role this fruit plays in the lives of millions around the globe. Beyond the supermarket shelves, bananas are a cornerstone of diets, a driving force in economies, and deeply woven into the cultural fabric of communities worldwide. Let's start with the dinner table. For many of us in the Western world, the banana is a convenient snack or a sweet treat. But across vast stretches of the globe, particularly in tropical and subtropical regions, bananas are a dietary staple, providing essential nutrients and a significant portion of daily calories. In Uganda, mataka, a dish made from steamed green bananas, isn't just a national dish, it's the primary source of carbohydrates for many. Across South and Southeast Asia, the banana's versatility shines. It finds its way into savory curries, sweet desserts, crispy chips, and even alcoholic beverages. In India and China alone, a staggering 26% of the world's bananas were grown in 2022, highlighting the fruit's significance in these nations. This culinary adaptability, the ability to be both sweet and savory, has secured the banana a central place in countless culinary traditions. Beyond sustenance, bananas are deeply intertwined with cultural practices. They're more than just food, they're symbols, offerings, and even building materials. In some cultures, bananas feature prominently in religious ceremonies and festivals. In others, they're tokens of hospitality, presented as gifts to welcome guests. And it's not just the fruit itself. The Iban people of Borneo, for example, demonstrate the banana plant's remarkable utility. They consume the flower buds as a vegetable, eat the young fruits raw after salting them like cucumbers, and even use the soft inner stems for sustenance. The leaves, too, find diverse applications, serving as plates, wrapping material, and even roofing in some regions. Fibers extracted from the plant are transformed into textiles, paper, and rope, showcasing the ingenuity of communities in utilizing every part of this remarkable plant. This deep connection to the banana plant translates directly into economic reliance. The banana industry is a global economic engine, a multi-billion-dollar trade that sustains livelihoods from the smallest farms to the largest corporations. Millions depend on the banana, from the farmers who cultivate it to the workers who pack and ship it, and finally to the retailers who sell it. For entire nations, particularly developing economies, bananas are a crucial export commodity, generating vital income that fuels local economies and creates jobs. Ecuador, Costa Rica, the Philippines, and Guatemala are just a few examples of countries whose economies are significantly tied to banana production and export. A small banana farmer in the Caribbean, for example, relies on their Cavendish banana harvest to support their family and contribute to their community. Their income, derived from sales to local markets and exporters, is directly linked to the health and productivity of their banana plants. But this economic engine, this source of sustenance and cultural significance, is facing a potential crisis. The Cavendish banana, the dominant variety in the global banana trade, is under threat. A new strain of Panama disease, a devastating fungal infection, is spreading, raising the specter of widespread devastation. This isn't just an abstract threat, it's a real and present danger with potentially catastrophic consequences. Imagine the ripple effect if this disease were to take hold. The Caribbean farmer, whose livelihood is tied to the Cavendish, could see their entire crop wither and die, leaving them without income and their family without support. This scenario, replicated across countless farms and communities, paints a stark picture of the economic hardship a Cavendish crisis could unleash. The economic impact wouldn't be confined to individual farmers. Entire economies, heavily reliant on banana exports, would face crippling revenue losses. Businesses would collapse, jobs would disappear, and the ripple effects would be felt throughout the global supply chain. The threat extends beyond economics to the very foundation of food security. For families in East Africa who depend on plantains, a close relative of the banana, as a dietary staple, a disease outbreak could be devastating. If their plantain crop were decimated, they would lose a crucial source of nutrition, facing the grim reality of food insecurity and malnutrition. This vulnerability underscores the precariousness of relying on a limited number of varieties in our food system. Just as the Gros Michel banana, the dominant variety in the early 20th century, was wiped out by an earlier strain of Panama disease, the Cavendish now faces a similar fate. This historical precedent highlights the dangers of monoculture farming, where vast tracts of land are dedicated to a single crop, leaving the entire system vulnerable to a single threat. The lack of genetic diversity in commercial banana production amplifies this risk, making it even more critical to explore and cultivate a wider range of banana varieties. The banana, then, is more than just a fruit. It's a lens through which we can examine the complex interplay of agriculture, economics, culture, and human well-being. It's a story of interconnectedness, a reminder that our food choices have far-reaching consequences. The Cavendish crisis isn't just a threat, it's a wake-up call. It's an opportunity to learn from the past, to rethink our approach to agriculture, and to build a more resilient and sustainable food system. It's a chance to embrace the incredible diversity of the banana world, from the tiny, seed-filled wild bananas to the plump, sweet Cavendish we know so well. It's time to invest in research, explore alternative varieties, and promote sustainable farming practices, not just to save a single fruit, but to create a more secure and diverse food future for all. What can you do? Support research, seek out diverse banana varieties when you shop, and become an advocate for a more sustainable and resilient food system. The future of the banana, and indeed the future of our food, depends on it. Chapter 5. Saving the Banana, a mission to preserve a global staple. We've discussed the banana's journey from its wild ancestors to the familiar fruit we find in grocery stores. But that journey faces a significant obstacle. You may have heard of the Gros Michel, the banana enjoyed by previous generations. It was wiped out by a fungal disease called Panama disease, or Fusarium wilt. This forced a switch to the Cavendish banana we eat today. But now, history is on the verge of repeating itself. A new strain of Panama disease, known as Tropical Race 4, or TR4, is spreading worldwide, and the Cavendish is vulnerable. However, scientists are determined to save the banana, using a toolkit of advanced techniques. One approach involves exploring the rich diversity of the Musa genus, which includes wild relatives of the Cavendish. These wild bananas often look and taste very different from the bananas we know, and many have hard, inedible seeds. But these seeds are of particular interest to scientists because they contain a wide range of genetic diversity, some of which could hold resistance to diseases like TR4. For example, Musa gracilis *, a small wild banana found in Malaysian rainforests, is a subject of research. Scientists aren't focused on its small, seed-filled fruit but rather its ability to thrive in its native habitat. Could its genes reveal secrets of resilience against pests or environmental stresses? Likewise, they're studying subspecies like Musa acuminata banksii *, which has contributed significantly to the genetic makeup of many cultivated bananas. Understanding how it resists disease might be crucial for creating hardier varieties. Banana breeding, however, is complex. Commercial bananas like the Cavendish are seedless, which means they don't reproduce sexually in the traditional way. They're essentially clones, propagated through suckers that grow from the parent plant's base. This lack of sexual reproduction makes it difficult to breed new varieties. So, how do you create new bananas without seeds? This is where seed banks play an essential role. These collections preserve banana germplasm, or the plant's genetic material, from wild and cultivated bananas worldwide. Scientists can access these collections, carefully extracting seeds from wild varieties to use in breeding programs. They search for specific traits, like resistance to TR4, tolerance to drought or salinity, and even improved nutritional qualities. The breeding process is intricate. Bananas have a unique genetic feature. Chloroplast DNA, which is important for photosynthesis, is inherited from the mother, while mitochondrial DNA, involved in energy production, comes from the father. Understanding these inheritance patterns is vital for successful breeding. In addition to traditional breeding, scientists are also turning to gene editing. One promising advancement is a genetically modified Cavendish with increased resistance to TR4. By inserting a gene from a wild banana variety, researchers have boosted the Cavendish's ability to resist the fungus. However, gene editing isn't a complete solution. Resistance can weaken over time as the fungus adapts, and acceptance of genetically modified foods varies widely. This brings up another challenge: consumer preferences. We're used to the Cavendish, its predictable size, shape, and taste, so introducing new varieties can be challenging. Imagine bananas like the bright red Dhaka, with its slightly tangy flavor, or the tiny, sweet ladyfinger. These offer a glimpse of the banana's diversity, but getting them onto grocery store shelves and into shopping carts means overcoming the public's attachment to the familiar Cavendish. For instance, the gummy texture of the red Dhaka might be off-putting to some, and certain Chinese varieties have an intense aroma that might overwhelm others. Even the thin skin of the Mysore banana, while easier to peel, raises concerns about bruising during transport. Scientists are working on addressing these issues, breeding varieties that combine disease resistance with consumer-friendly traits. Public education is also essential. By highlighting the remarkable diversity of bananas and showcasing their unique flavors and nutritional benefits, we can encourage broader appreciation and demand for these resilient varieties. The future of bananas likely depends on embracing diversity. Just as we enjoy many types of apples, like Granny Smith and Fuji, we may soon see a rainbow of bananas in our fruit bowls. This shift won't happen overnight. It will take cooperation among scientists, farmers, retailers, and consumers. But the stakes are high. Bananas are a staple food for millions, and losing them would be devastating. By supporting scientific innovation and expanding our acceptance of different banana varieties, we can help ensure that this beloved fruit continues to thrive for generations to come. Chapter 6. Beyond the Cavendish, a world of banana diversity. Get ready to embark on a global banana expedition, a journey far beyond the familiar yellow Cavendish. While the Cavendish reigns supreme in supermarkets, it's just one note in a vibrant symphony of banana diversity. Imagine bananas that taste like vanilla ice cream, tangy apples, or even something reminiscent of a baked potato. Imagine textures from silky smooth to delightfully chewy. This is the world of banana diversity, a world brimming with culinary treasures and genetic wonders waiting to be explored. Let's start our culinary adventure in Southeast Asia, a region where the line between dessert and cooking bananas blurs into a delicious spectrum. In countries like India, the musa, Nendrin, cultivar isn't just a banana, it's a cultural icon. Widely grown in Kerala, the Nendrin is prized for its unique flavor profile, a delicate balance of sweet and tangy with a hint of tartness. This distinct flavor makes it a cornerstone of Kerala cuisine, starring in dishes like Nendrin chips, a crispy, savory snack, and Nendrin pasam payasam, a creamy, sweet pudding often served during festivals and celebrations. This banana isn't just food, it's woven into the fabric of Kerala's cultural heritage, a symbol of tradition and communal celebration. Similarly, in the Philippines, the Latundan banana is a culinary chameleon. Eaten green, it provides a starchy base for savory dishes. As it ripens, its sweetness intensifies, transforming it into a delightful dessert banana, eaten fresh or used in sweet treats. This adaptability highlights the versatility of bananas and their integral role in providing both sustenance and culinary delight. The red Dhaka banana, with its striking reddish-purple peel, further exemplifies the culinary diversity of Southeast Asian bananas. Its sweet, tangy flavor lends itself beautifully to both raw consumption and cooked applications, adding a vibrant pop of color and a unique flavor dimension to local dishes. Our exploration wouldn't be complete without venturing into the wild, where the ancestors of our cultivated bananas thrive. Scientists aren't just admiring these wild relatives, they're delving into their genetic secrets, hoping to unlock traits that could revolutionize the future of bananas. Species like Musa acuminata and Musa balbisiana, the wild parents of many cultivated varieties, hold a treasure trove of genetic diversity. Researchers are meticulously studying their genomes, searching for genes that confer resistance to diseases like Fusarium wilt, a devastating fungal disease that poses a significant threat to global banana production. These wild bananas often contain numerous seeds, unlike their seedless cultivated counterparts. These seeds are not just a culinary inconvenience, they're genetic time capsules, containing the blueprints for a vast array of traits, from disease resistance to drought tolerance and enhanced nutritional content. By identifying and isolating these beneficial genes, scientists hope to introduce them into cultivated varieties, creating bananas that are not only delicious but also resilient to the challenges of a changing world. This genetic exploration is aided by the existence of banana gene banks, repositories of banana germplasm from around the world. These gene banks serve as living libraries of banana diversity, preserving valuable genetic material for future research and breeding efforts. They act as a safeguard against the loss of genetic diversity, ensuring that the building blocks for future banana varieties are readily available. By conserving these wild relatives and their diverse genetic makeup, we're not just preserving the past, we're investing in the future of bananas. The study of wild bananas also reveals fascinating insights into their evolutionary history and the unique ways they pass on their genes. Bananas exhibit an unusual pattern of genetic inheritance. Chloroplast DNA, essential for photosynthesis, is inherited maternally, meaning it's passed down solely from the mother plant. Mitochondrial DNA, responsible for energy production, follows a different path, inherited paternally from the father plant. These distinct inheritance patterns provide powerful tools for researchers, allowing them to trace the lineage of different banana varieties and unravel their evolutionary relationships. By analyzing the chloroplast and mitochondrial DNA of different banana species, scientists can construct family trees, tracing the ancestry of cultivated bananas back to their wild origins and understanding how they've diversified and adapted over millennia. This knowledge is invaluable for breeding programs, enabling scientists to select parent plants with desirable traits and predict the inheritance patterns of those traits in their offspring. This genetic detective work is revealing the complex interplay of genes that shape banana diversity. For example, researchers have identified specific genes in Musa acuminata subspecies that contribute to the different subgenomes found in triploid cultivated bananas. This understanding of banana genetics is not just an academic exercise. It's a crucial step towards developing new varieties that are better adapted to changing environmental conditions and resistant to emerging diseases. The world of banana diversity extends far beyond the familiar Cavendish. The blue Java, aptly nicknamed the ice cream banana, offers a soft, creamy texture and a pronounced vanilla flavor, a natural fit for desserts and smoothies. The Chinese banana, with its potent aroma that can supposedly be detected from miles away, adds a unique sensory dimension to the banana experience. And for those seeking a truly wild encounter, the Musa gracilis of peninsular Malaysia, with its small, seed-filled fruits, offers a glimpse into the ancestral origins of bananas. These lesser-known varieties are not just culinary curiosities, they're genetic goldmines. Each variety holds a unique set of traits, a potential source of disease resistance, improved nutritional value, or novel flavors. As we face the looming threat of diseases like Panama disease, the diversity within these lesser-known bananas offers a beacon of hope. By exploring and utilizing this diversity, we can develop new, resilient varieties that can withstand the challenges of climate change and emerging diseases, ensuring that bananas remain a staple food for generations to come. This exploration also sheds light on the culinary ingenuity of cultures around the world. From banana curries and fritters to puddings and chips, these varieties are not just ingredients, they're integral components of local cuisines, reflecting the diverse culinary traditions and cultural heritage of different regions. For example, the Fiji bananas of Polynesia, with their vibrant orange flesh and unique flavor profile, are a testament to the adaptability of both bananas and the people who cultivate them. These bananas, genetically distinct from the more common varieties, have evolved to thrive in the specific conditions of the Pacific Islands, providing a vital source of sustenance and cultural identity. Similarly, the Insete ventricosum, or false banana, of Africa, is a staple food crop in Ethiopia, providing not only food but also fiber for rope and construction materials. This diversity is not confined to remote corners of the world. You might be surprised to find some of these lesser-known varieties in your local specialty food store or farmer's market. By seeking out and enjoying these diverse bananas, we're not just expanding our palates, we're actively supporting the preservation of biodiversity, a crucial step towards ensuring the long-term health of our planet and the resilience of our food systems. Imagine a world where bananas come in a rainbow of colors and flavors, a world where each bite offers a new and exciting culinary adventure. This isn't just a dream, it's a possibility within our reach, a future where the banana landscape is as diverse and vibrant as nature intended. By embracing the full spectrum of banana diversity, we can celebrate the rich tapestry of flavors, cultures, and genetic wonders that this remarkable fruit has to offer. Chapter 7. Guardians of Diversity, Botanical Gardens and the Banana's Fate. Imagine a world where bananas come in a rainbow of colors, scarlet, pink, even blue, and offer a spectrum of flavors, from vanilla ice cream to an aroma so potent it can be detected from a distant mountain. This isn't a fantasy, but a testament to the remarkable diversity within the banana family, a diversity now facing a precarious future. In this vital conservation effort, botanical gardens, particularly institutions like Kew, emerge as critical guardians. These gardens serve as living repositories of plant life, safeguarding the genetic heritage of countless species, including the banana. They're not merely beautiful landscapes but dynamic centers of research, conservation, and education, holding the key to preserving the vast range of banana varieties most of us have never encountered. Kew, for instance, stands at the forefront of this endeavor. Recognizing that lesser-known species may hold the genetic solutions to the challenges plaguing commercial banana production, Kew actively collects and protects wild relatives of the banana. It's akin to creating a genetic backup plan, a reservoir of traits that could equip future bananas to withstand diseases, pests, and the shifting climate. This essential conservation work, however, is far from simple. One significant hurdle is the sheer magnitude of banana varieties. With over 1,000 types, from the ubiquitous Cavendish to the exotic Musa gracilis, a small, seeded banana native to Malaysia adorned with pink and purple flowers, the task of tracking, collecting, and preserving such a broad spectrum demands substantial resources, expertise, and global collaboration. The banana's own biology presents another layer of complexity. Many commercial bananas, like the Cavendish, are seedless, reproducing through offshoots, essentially clones of the parent plant. This characteristic hampers traditional breeding methods, which rely on seeds to generate new gene combinations. It's comparable to attempting to craft a new recipe without the ability to blend diverse ingredients, a conundrum faced by scientists working with seedless bananas. To address this, Kew and other botanical gardens have turned their attention to wild banana species, many of which do produce seeds. These wild relatives, such as Musa acuminata ssp. Acuminata and E. livingstonianum, are being studied and preserved as part of Kew's Crop Wild Relatives project. They represent a treasure trove of genetic diversity, potentially offering disease resistance, drought tolerance, and other desirable traits that could be introduced into cultivated bananas. Working with wild species, however, brings its own set of challenges. Some are rare and elusive, thriving in remote, inaccessible locations. The Musa gracilis, for example, is found in the ravines of Malaysia, requiring dedicated, location scouting by researchers like Anthony Basil Rodriguez. He describes his quest for this wild banana as a very interesting story, underscoring the effort and commitment involved in gathering these invaluable genetic resources. Furthermore, preserving these wild species necessitates specialized facilities and expertise. Banana plants, large, fast-growing herbs rather than trees, require specific conditions to flourish. Their vulnerability to chilling injury, wind damage, and drought makes their cultivation and long-term preservation a delicate balancing act, akin to replicating a tropical rainforest within a greenhouse. The banana's narrative transcends a simple fruit. It reflects our relationship with the natural world. The dominance of the Cavendish, a single variety among thousands, highlights the homogenization of our food system, prioritizing efficiency and uniformity at the cost of resilience and diversity. The potential demise of the Cavendish due to Panama disease serves as a stark warning about the perils of monoculture farming and the critical need to preserve genetic diversity. Botanical gardens like Kew are not passive storehouses of plant life but active players in the struggle to secure our food's future. Their race against time to collect, study, and preserve the banana's wild relatives acknowledges these unsung heroes of the banana family as potential saviors of a more diverse and resilient banana landscape. Their work is a multifaceted endeavor, a race against a devastating disease, a testament to the importance of biodiversity, and a fight for the future of a staple food. The challenges are substantial, but the stakes are even higher. The banana is a cornerstone of diets for millions globally, a source of livelihood for countless farmers, and a cultural symbol. The efforts of botanical gardens to preserve banana diversity transcend the preservation of a single fruit. They encompass safeguarding livelihoods, ensuring food security, and protecting a vital piece of our global heritage. It's a recognition that the banana's future, and perhaps the future of our food system, rests on the diversity we protect today. Consider the Gros Michel, once the dominant banana in global trade. It possessed a creamy texture and a richer flavor compared to the Cavendish. However, a fungal disease, Panama disease, decimated Gros Michel plantations, leading to its near extinction in commercial production. This historical precedent underscores the vulnerability of relying on a single variety and the devastating consequences of lost diversity. The Cavendish, the banana we commonly find in supermarkets, emerged as the Gros Michel's successor, chosen for its disease resistance to the strain prevalent at the time, its ability to withstand long journeys, and its suitability for large-scale production. However, a new strain of Panama disease, tropical race 4, has emerged, threatening the Cavendish in a similar manner to its predecessor. This new threat highlights the ongoing vulnerability of monocultures and the urgent need for diversified banana production. The Cavendish banana's susceptibility to this new strain of Panama disease is largely due to its method of cultivation. Because Cavendish bananas are seedless, they are propagated through offshoots, creating genetically identical plants. This lack of genetic diversity means that if one plant is susceptible to the disease, all plants are susceptible. This vulnerability underscores the limitations of relying on a single variety and the importance of genetic diversity in building resilience against disease. The current situation facing the Cavendish banana parallels the earlier crisis with the Gros Michel, demonstrating the cyclical nature of these challenges in monoculture systems. The lack of genetic diversity creates a vulnerability to disease, and a reliance on a single variety amplifies the potential impact of an outbreak. The banana's story serves as a cautionary tale, highlighting the need for a more diverse and resilient approach to food production. Botanical gardens, in their role as preservers of plant diversity, are actively working to prevent a repeat of the Gros Michel tragedy. Their efforts to collect and conserve wild banana varieties offer a potential solution. These wild relatives hold a wealth of genetic diversity that could be used to breed new, disease-resistant banana varieties, offering a more sustainable future for banana production. The challenges in preserving banana diversity, however, extend beyond the biological. The very nature of the banana industry, with its emphasis on uniformity and standardization, creates hurdles for diversifying production. Consumers are accustomed to the Cavendish banana's specific size, shape, and flavor, and introducing new varieties may require shifts in consumer preferences and market demands. Furthermore, the economic realities of banana production, particularly in countries heavily reliant on banana exports, create additional challenges. Shifting to new varieties may require investment in new infrastructure and farming practices, potentially impacting livelihoods and economic stability in these regions. Balancing the need for diversity with the economic realities of banana production is a complex issue that requires careful consideration. Despite these challenges, the work of botanical gardens in preserving banana diversity offers a beacon of hope. By safeguarding the genetic heritage of the banana family, these institutions are providing a crucial resource for researchers and breeders working to develop a more sustainable future for this important crop. Their efforts are a testament to the power of biodiversity and the importance of preserving the natural world for future generations. Chapter 8. The banana industry's footprint, environmental and social impacts. Our journey through the banana's story wouldn't be complete without acknowledging the complex relationship between the industry, the environment, and the communities it touches. While bananas bring joy to our breakfast tables and smoothies, their production has left a significant mark on the world, a mark we need to understand to build a more sustainable future for this beloved fruit. The industry's impact on forests is a major concern. The demand for vast banana plantations has driven deforestation in some regions, converting diverse ecosystems into monoculture landscapes. This isn't just about losing trees, it's about the ripple effect this has on entire ecosystems. For example, in Malaysia, clearing land for banana plantations fragments the habitat of the endemic Musa gracilis, a wild banana species, pushing it closer to the brink. This habitat loss also affects the animals that depend on these forests, like the orangutans of Borneo, whose already dwindling habitat is further threatened by agricultural expansion. The conversion of diverse rainforests, rich with a multitude of plant and animal species, into a sea of identical banana plants represents a drastic reduction in biodiversity, impacting the delicate balance of the environment and making it more vulnerable to pests and diseases. Beyond deforestation, several unsustainable farming practices take a toll. The relentless drive for high yields and low costs has led to the overuse of agrochemicals like pesticides and fungicides. While these chemicals offer short-term protection against pests and diseases like black sigatoka, a fungal leaf spot disease that can significantly reduce yields, they have long-term consequences. These chemicals can leach into the soil and contaminate water sources, harming aquatic life and potentially entering the food chain. In Hawaii, for example, the invasive banana poca vine, Passiflora tarminiana, which smothers native trees, is further spread by non-native animals that consume its fruit, highlighting the interconnectedness of these environmental challenges. Furthermore, the heavy reliance on chemical fertilizers depletes soil nutrients, leading to soil degradation and decreased productivity over time. This creates a vicious cycle where more chemicals are needed to maintain yields, further exacerbating the environmental damage. Other unsustainable practices include intensive irrigation, which can deplete water resources, and the improper disposal of plastic sheeting used on plantations, contributing to plastic pollution. The focus on a single banana variety, the Cavendish, has magnified these issues. Its genetic uniformity makes it incredibly susceptible to diseases like Panama disease, caused by the Fusarium oxysporum F. sp. Cubens fungus. The Cavendish's susceptibility has created a dangerous dependence on chemical treatments to combat this devastating disease. The fungus, which persists in the soil for decades, enters the plant through the roots and blocks the vascular system, effectively choking the plant and causing it to wilt and die. This reliance on chemicals not only harms the environment but also poses significant health risks to farm workers and their families. Exposure to these agrochemicals can lead to a range of health problems, including skin irritation, respiratory issues, neurological disorders, and even certain types of cancer. Children are particularly vulnerable to the harmful effects of pesticide exposure. However, there is hope. A growing movement towards sustainable banana production is gaining momentum. Farmers are exploring alternative pest control methods, such as introducing beneficial insects that prey on banana pests or using biopesticides derived from natural sources. Crop rotation, intercropping with other plant species, and the use of organic fertilizers are also being adopted to improve soil health and reduce reliance on synthetic inputs. Organizations like the Rainforest Alliance and Fair Trade International are working to certify banana farms that meet specific environmental and social standards, promoting practices that protect wildlands, wildlife, and water resources while also improving the quality of life for farmworkers. Other organizations, such as the Pro-Musa Network and Biodiversity International, are conducting research and promoting the conservation and use of wild banana varieties, which hold valuable genetic traits for disease resistance and other desirable characteristics. Imagine a banana plantation integrated within a thriving ecosystem, where biodiversity flourishes and agricultural practices work in harmony with nature. This is the vision driving these sustainable initiatives. The story of the Cavendish banana, a successor to the Gros Michel, which was wiped out by an earlier strain of Panama disease, Race 1, is a cautionary tale. While the Cavendish thrived initially due to its Race 1 resistance, long shelf life, and suitability for export, it now faces its own demise at the hands of tropical Race 4, TR4, a new strain of the same fungus. This reinforces the dangers of relying on monocultures and highlights the urgent need for diversification. The economic implications of these challenges are profound. Banana-producing countries in Latin America and the Caribbean, where banana exports are a pillar of the economy, face substantial economic losses if the Cavendish is lost. Colombia's declaration of a national state of emergency in 2019 after TR4 was detected on its banana farms illustrates the severity of the threat. The Cavendish accounts for almost all global banana exports, a market valued at around $10 billion annually. If TR4 spreads unchecked, the economic consequences for these countries could be devastating, leading to job losses, reduced export earnings, and social unrest. The search for a Cavendish replacement is ongoing, but finding a variety that satisfies multinational buyers is proving challenging. The FHIA-18, for example, while resistant to TR4, has not been widely adopted due to its smaller size, different flavor profile, and slightly shorter shelf life, characteristics that deviate from the Cavendish's established market appeal. Multinational buyers prioritize consistency in size, appearance, flavor, and transportability, making it difficult to introduce new varieties, even if they offer disease resistance. The banana industry's situation parallels challenges faced in the tech world. Just as monoculture banana plantations are vulnerable to disease, homogeneous software systems are susceptible to widespread attacks. The Morris worm of 1988, which rapidly infected a large percentage of internet-connected computers, and the Mirai botnet of 2016, which disrupted major online services, demonstrate the risks of uniformity in computer systems. In response, the tech industry has developed strategies to introduce artificial diversity into software. One approach, implemented by Microsoft in Windows OS, involves randomizing internal data storage locations, making it harder for malware to exploit vulnerabilities consistently across all systems. These strategies offer valuable insights for agriculture. Just as software diversity enhances resilience against attacks, cultivating a wider range of banana varieties can safeguard against widespread crop failure due to disease. By diversifying banana production and incorporating disease-resistant varieties, we can create a more resilient and sustainable banana industry. The banana's story is more than just a tale of a fruit. It's a reflection of our relationship with the environment, the global food system, and the choices we make as consumers. The challenges facing the banana industry, deforestation, unsustainable farming practices, disease, and economic vulnerability, highlight the interconnectedness of these issues. But the growing movement towards sustainable production, coupled with innovative approaches inspired by other fields like technology, offers hope for a more equitable and environmentally sound future for this beloved fruit. By understanding the industry's footprint and supporting sustainable initiatives, we can contribute to a more resilient banana industry that benefits both people and the planet. Chapter 9. Decoding the Banana's Family Tree, a Journey Through Evolution in Genetics. Bananas, those convenient, brightly colored fruits we often take for granted, harbor a rich and complex history, a story etched in their DNA and whispered through the rustling leaves of their wild ancestors. It's a tale of tropical origins, human intervention, and an ongoing struggle for survival against the backdrop of a changing world. Our journey begins not in the sterile aisles of a supermarket, but in the vibrant, humid heart of tropical Asia, the birthplace of the wild bananas. We're talking about species like Musa acuminata and Musa balbisiana *, the two progenitors of most of the bananas we eat today. Picture them. Musa acuminata *, perhaps a bit smaller than the bananas we're used to. Its fruit speckled with numerous hard seeds, thriving in the dappled sunlight of the Southeast Asian rainforest. Nearby, Musa balbisiana *, robust and sturdy, stands tall, its fruit also bearing seeds, but offering a different flavor profile, a hint of the starchy heartiness we find in today's plantains. But the story doesn't end there. The banana family tree branches out in countless directions, encompassing a dazzling array of wild species. There's Musa gracilis *, a delicate beauty endemic to the Malaysian peninsula, its pink and purple flowers a testament to nature's artistry. Then there's the colossal Musa ingens *, the largest herbaceous plant on Earth, hidden deep within the jungles of West Papua. Imagine trekking for days through dense rainforest, as botanist Joseph Simcox did, only to stumble upon this giant, its massive pseudostem reaching for the sky, a testament to the sheer scale and diversity of the banana family. Other wild species like the scarlet banana, Musa coccinea *, with its vibrant red bracts, the pink banana, Musa velutina *, sporting equally striking pink fruits, Musa mani * from the remote forests of Arunachal Pradesh, and Musa bakeri * from the island of Borneo, each add their unique brushstrokes to this botanical tapestry. And then there are the Fii bananas, a group genetically distinct from other bananas, their fruits a vibrant array of colors, from orange to purple, cultivated and cherished by Pacific Islander communities for centuries. These wild bananas aren't just interesting curiosities, they're a vital genetic reservoir, holding the potential to unlock disease resistance, improve fruit quality, and adapt to changing climates. Some, like Musa coccinea and Musa velutina *, are already appreciated for their ornamental value, adding a touch of the exotic to gardens around the world. Others, like the Fii bananas and many of the Bornean species, are important food sources for indigenous populations, their fruits and flower buds providing sustenance and cultural significance. The genetic story of bananas is just as captivating as their geographic spread. The familiar, seedless bananas we find in supermarkets are often triploids, meaning they have 3 sets of chromosomes instead of the usual 2. This triploidy, a result of ancient hybridization events between wild species, is the reason for their lack of seeds. It's a genetic quirk that's both a blessing and a curse. Seedlessness makes bananas incredibly convenient to eat, but it also throws a wrench in the works when it comes to traditional breeding. Imagine trying to cross 2 plants that don't produce seeds. It's a genetic dead end. The complexity deepens when we look at the inheritance of chloroplast and mitochondrial DNA in bananas. In most plants, both types of DNA are inherited from the mother. But bananas break the mold. While their chloroplast DNA follows the usual maternal inheritance pattern, their mitochondrial DNA is surprisingly passed down from the father, a genetic anomaly that intrigues scientists and offers clues to their evolutionary past. This unusual inheritance pattern has implications for tracing banana lineages and understanding the contributions of different wild ancestors to modern cultivars. Speaking of cultivars, the diversity within the banana family extends far beyond the ubiquitous Cavendish. While we may only see a handful of varieties in our local stores, there are over 1,000 different kinds of bananas cultivated and consumed around the world. Plantains, often mistaken for a different fruit altogether, are actually just another branch of the banana family tree. Their genetic makeup is often designated by combinations of A and B genomes, reflecting their mixed ancestry from Musa acuminata and Musa balbisiana. For example, the French plantains, with their persistent male flowers, are typically AAB, while horn plantains, lacking male flowers, are often AB. These genetic variations translate into a wide range of flavors, textures, and cooking properties. The AAB plantains, like the popular Nendrin cultivar from India, tend to be sweeter and less starchy than the AB types, like the Blugo from the Caribbean, which are prized for their savory flavor and ability to hold their shape when cooked. This brings us to the fascinating world of banana taxonomy, the science of classifying and naming organisms. Bananas belong to the genus Musa *, part of the family Musaceae, which in turn falls within the order Zingiberales. This order also includes other familiar tropical plants like ginger, heliconia, and bird of paradise, hinting at the shared ancestry and evolutionary relationships within this botanical group. Even the great Carl Linnaeus, the father of modern taxonomy, grappled with classifying bananas. He initially divided them into just two species, Musa sapientum * for dessert bananas and * Musa paradisiaca * for plantains, based solely on their culinary uses. Little did he know the genetic complexity that lay beneath the surface. Later research, using genetic analysis, revealed the true parentage of cultivated bananas, tracing their lineage back to the wild Musa acuminata and * Musa balbisiana. Unraveling the banana's evolutionary history is no easy task. One of the challenges lies in the difficulty of preserving banana specimens for taxonomic study. The large, fleshy nature of banana plants makes them notoriously difficult to prepare as herbarium specimens, the dried, pressed plants used for botanical research. Imagine trying to flatten a giant banana leaf or preserve the delicate structure of a banana flower. It's a botanical battle against decay and distortion. This difficulty in creating lasting records has hampered our ability to study the diversity of bananas throughout history and understand how different species have evolved and diverged over time. The seedless nature of most cultivated bananas has forced humans to develop ingenious methods of propagation. Instead of relying on sexual reproduction, bananas are propagated vegetatively, using suckers that sprout from the base of the parent plant. Farmers carefully select these suckers, detach them from the mother plant, and replant them, creating a new generation of genetically identical bananas. This method is efficient and ensures consistency, but it also creates monocultures, vast plantations of genetically uniform plants. And as we've seen with the devastating spread of Panama disease, this lack of genetic diversity can be a recipe for disaster. The research also highlights another, less obvious consequence of vegetative propagation. As forests are cleared for agriculture and other human activities, formerly isolated populations of wild bananas are now growing side by side along roadsides and in disturbed habitats. This proximity allows for cross-pollination between previously isolated subspecies, leading to genetic mingling and the potential loss of unique genetic traits. The story of banana evolution isn't just a scientific curiosity, it's a cautionary tale with real-world implications. The threat of Panama disease, a soil-borne fungus that decimated Gros Michel banana plantations in the last century and is now threatening the Cavendish, underscores the fragility of our reliance on a single banana variety. Understanding the banana's evolutionary history, its genetic diversity, and the complexities of its reproductive biology is crucial for developing sustainable solutions. Scientists are working tirelessly to identify disease-resistant varieties, exploring the genetic wealth of wild bananas and developing new breeding techniques to overcome the challenges of triploidy and seedlessness. The future of the banana depends on our ability to learn from the past, embrace diversity, and work in harmony with nature to ensure that this beloved fruit continues to grace our tables for generations to come. Our exploration into the world of bananas reveals essential insights into the impact of monoculture farming, the benefits of genetic diversity, and the importance of sustainable practices. The reliance on a single variety, like the Cavendish, exposes the banana industry to significant risk, as shown by the devastating effects of Panama disease, which wiped out the Gros Michel and now threatens the Cavendish. This reliance highlights the need for a broader genetic base in agriculture to build resilience against diseases and environmental changes. Researchers are now turning to wild banana species for solutions, discovering genetic traits that may offer natural resistance to diseases or even new, exciting flavors. These wild species represent a crucial resource for developing future banana varieties that can withstand challenges while reducing the need for chemical interventions. Sustainable farming methods are also gaining attention, focusing on reducing deforestation, minimizing chemical use, and protecting biodiversity, efforts that benefit both ecosystems and local communities. Looking forward, the work in genetic diversity and sustainable practices sets a strong foundation for the future of agriculture. Innovations in crop genetics and eco-friendly farming could provide a more resilient food supply that adapts better to environmental pressures. Although the banana is our focus here, these strategies can apply to many crops, encouraging a food system that values both diversity and sustainability. As we wrap up, we'd love to hear your thoughts. What surprised you most, and what other crops should we explore next? Leave a comment below, and if you enjoyed this journey, please like, subscribe, and share. Thank you for watching, and remember, curiosity fuels discovery, and there's always more to learn.